Hi students, welcome to Sankalp Study Success. I am Tirupati Rao. Today I am going to, please subscribe our channel. Today I am going to discuss about radial probability distribution curves. In the previous videos, we are discussed about plotting between psi and radial distance and psi square and also radial distance. But in this video, we will discuss about radial probability. Right? So what is the radial probability? So this is the nucleus. This is the atom. This is the nucleus. This is the nucleus, and this is the orbit. So here the electron is present. Here the electron is revolved around the nucleus in circular path. So this is its radius is r, and this is the one spherical. Its radius is dr. Its radius is dr. So we know that orbital, the probability of finding electron around the nucleus is maximum. That is, the maximum probability of finding electron around the nucleus in 3-dimensional space is taken as orbital. But radial probability, the probability of finding electron within the spherical shell at a distance between the r and r plus dr from the nucleus. So here we can calculate the finding of electron in this spherical volume. So between the r and r plus dr. So this is what its radius, r. What its radius? This is r and this is dr, r plus dr. So here in this diagram we can find the probability of finding electron in the r, between the r and r plus dr volume, right? So the probability of finding electron within the spherical shell, between the r and r plus dr from the nucleus. So this is the radial probability, is known as radial probability. That means the probability of finding electron in the small spherical volume is known as simply radial probability. So radial probability is equal to radial probable density into volume of the spherical shell. Radial probability is represented by D, capital D. Radial probability is represented by capital D, right? So is equal to radial probability density into volume of spherical shell. So in the previous video, we will discuss about radial probable density. Radial probable density is like a psi square or r square. So radial probable density is psi square or r square. So this is the radial node. This is dependent upon radial distance and NL. But the angular nodes, in the previous video already discussed, the angular nodes or nodal plane is dependent upon the angle theta pi and also Lm quantum numbers. Here radial nodes is dependent upon the principal quantum number and azimuthal quantum number with radial distance. But angular node is dependent upon angle like theta pi with quantum numbers. Which quantum numbers? L and M. So L means L gives a shape of the orbital. That means angular nodes tells the shape of orbital. Angular node gives the information about shape of orbital, but radial nodes does not gives the shape of orbital. Okay, angular node gives the information about shape of the orbital, but radial nodes cannot give the information about shape of orbital. Suppose shape of orbital, S orbital is a spherical, P orbital is a dumbbell. That now a radial probability is equal to, what is the formula? Radial probability is represented by D. Radial probability D is equal to radial probability density into volume of spherical shell. So a radial probability density is represented by r square or psi square into volume of spherical cell. This volume of spherical cell we can say V. So we know that the volume of sphere is 4 by 3rd pi r cube. 4 by 3rd pi r cube. This is the volume of r radius sphere. If you want to volume of r plus dr sphere, this is the r plus dr sphere. What its volume? 4 by 3rd pi. What its radius? R plus dr whole cube. If you want to volume of this only, if you want to volume of this small circle, what its volume? So 4 by 3rd pi into r plus dr whole cube minus 4 by 3rd pi r cube. This is the volume of the spherical cell. This is the volume of the spherical cell. So this volume is also calculated another method. What its this is the one sphere. What its surface area? Surface area into distance is like a volume. Surface area of sphere and its spherical cell distance is also taken as volume. So r square or psi square, both are same. R square and what its volume? Surface area of sphere. Surface area of sphere is 4 pi r square. We know that. What is the surface area of sphere or area of sphere? 4 pi r square into its distance. Distance of spherical cell, distance of length of spherical cell, how much? dr. So this is also taken as the volume of spherical cell. This is also taken as volume of spherical cell into dr. So finally we can write 4 pi r square dr into r square like NL or 4 pi r square dr or psi square. R square and psi square both are same. That is the radial probability density. Probability of finding electron around the nucleus is taken as orbital. That is represented by psi square. That is the radial probability density, psi square or r square. Now this is the formula of radial probability. D is equal to 4 pi r square dr into psi square. Now if we draw a graph between D means radial probability, like 4 pi r square into dr into psi square or r square, both are same. This is also taken as D and radial distance per 1s orbital, per 2s orbital, per 3s orbital, per 2p orbital, per 3p and 3d orbital. Now please observe this. So here what is the radial distribution, radial probability distribution curves? The curves are obtained by plotting between radial probability and radial distance from the nucleus is known as radial probability distribution curves. What is that? Radial probability distribution curves. What is radial probability distribution curves? Radial probability distribution curves is a curves which are obtained by plotting between radial probability like a D and radial distance from the nucleus, like a R. So this is the radial probability distribution curves. So in radial probability distribution curves, the radial probability distribution is increases with radius and reaches to maximum, and later it was decreases, Suppose we can take in a tree like a mango tree. ఓకే, ఒక మామిడి చెట్టు తీసుకుంటే రైట్. సో దీనిలో సరౌండింగ్లో రైట్, ఓకే, ఇది ఒక చెట్టు అనుకుంటే, ఒక మ్యాంగో చెట్టు అనుకుంటే, దీని సరౌండింగ్లో ఇలా మనం సరౌండింగ్ రీజన్స్ తీసుకుంటే దీని బేస్లో, సో ఈ మ్యాంగోస్ అనేవి సో ఇక్కడ తక్కువ పడే అవకాశాలు ఉంటాయి, అలాగే ఇక్కడ ఎక్కువ ఉంటాయి, అలా ఇంకా ఇక్కడ ఎక్కువ ఉంటాయి. ఆ తర్వాత ఏమవుతాయి, డిస్టెన్స్ దిస్ ఇస్ ద అవుటర్ బౌండరీ ఆఫ్ ట్రీ, సో లెస్ ఉంటాయి, చాలా తక్కువగా ఉంటాయి. అంటే ఇది ఒక ట్రీ తీసుకుంటే దాని బేస్లో ఏముండవు, చాలా తక్కువగా ఉంటాయి బేస్లో. అలాగా దాని సరౌండింగ్ చూసుకున్నట్లయితే, దాని సరౌండింగ్ రీజియన్స్ తీసుకున్నట్లయితే అలాగే ఇంక్రీజ్ అవుతాయి. మళ్ళీ ఆ చెట్టు బయట బౌండరీ తీసుకున్నట్లయితే ఆ మ్యాంగోస్ అనేవి తక్కువగా ఉంటాయి. సో దీన్ని బట్టి మనకి ఏమర్థమైందంటే, ఇక్కడ రేడియల్ ప్రాబబిలిటీ న్యూక్లియస్కి దగ్గరలో తక్కువగా ఉండి, అలాగా డిస్టెన్స్ ఇంక్రీజ్ అవుతుంటే ఆ రేడియల్ ప్రాబబిలిటీ ఇంక్రీజ్ అయ్యి, సో ఆ తర్వాత మ్యాక్సిమం రీచ్ అయ్యాయి, రేడియల్ ప్రాబబుల్ డిస్టెన్స్ అనేది మ్యాక్సిమం రీచ్ అయ్యి మళ్ళీ తర్వాత ఏమవుతుందంటే డిక్రీజ్ అవ్వడం జరుగుతుంది. సిమిలర్లీ దిస్ ట్రీ. సో ద రేడియల్ ప్రాబబిలిటీ is increases with radiance and reaches to maximum, and later it was decreases with increasing the radius for all graphs. So in these graphs, one curve is obtained, here 2 peaks are obtained, here 3 peaks are obtained. So listen to me. The number of peaks the number of peaks for radial distribution curves for an orbital is equal to n minus L. What is the formula? The number of peaks per radial distribution curves for an orbital is equal to n minus L, where n is the principal quantum number, L is the azimuthal quantum number. Suppose we can take in 1s orbital. So per 1s orbital, how many peaks are obtained per 1s orbital? N minus L. So what its n value? 1. What its L value? 0. 1 minus 0 is equal to 1. So how many peaks? One peak is present in our radial distribution curve of 1s orbital. Similarly, we can take in 2s. 2s means what its n value? 2 minus L means 0. Per s orbital L value 0. 2 minus 0 is equal to 2. How many peaks? One peak, second peak. 2 peaks are obtained. Similarly, we can take in 3s. How many peaks? So 3 minus 0 is got 3. So per 3s orbital 3 peaks are obtained. 1, 2, 3. So the number of peaks per radial distribution curves for an orbital is equal to n minus L. Now if you can take in 2p orbital, what its n value? 2. What its L value? 1. 2 minus 1 is equal to 1. So for 2p orbital, how many peaks are present? 1 peak is present. For 3p orbital, similarly we can take in 3p orbital. So 3 minus L minus 1 minus is equal to 3 minus 2 means 1. Right. 3p orbital. what is the number of peaks is equal to n minus l. 3p orbital is equal to n minus 3 minus l means 1. 3 minus 1 means 2. How many peaks? 2 peaks. Similarly 3d, for 3d orbital n value 3, d value, the l value per d orbital is 2. So 3 minus 2 is equal to 1. So 1 peak is present in a 3d orbital. Now listen to me. This is the formula of number of peaks for radial distribution curves per an orbital. This is the when the curve is touch on the x-axis. So that is said to be node. When the curve is reaches to or touching on the x-axis, that is said to be 0. That means probability of finding electron or radial distribution is equal to 0, that is said to be node. So here the probability, this peak is not touch on this x-axis, so here number of nodes is equal to 0. Here one peak, here distribution curve is touch on x-axis on one point. So here one node is present per 2s orbital. Similarly for 3s orbital, here 2 nodes, this is one, this is per another 2 nodes. This is not this curve is not touch on the x-axis, so this is not a node. So how many nodes per 3s orbital? 2 nodes. Okay, number of nodes, number of radial nodes. Number of radial nodes is equal to n minus l minus 1. Number of radial nodes is equal to n minus l minus 1. So what is n value? 3 minus l value per s orbital 0 minus 1. 3 minus 1 is equal to 2. So these are the 2 nodes per 3s orbital. So the diagrams for 1s orbital and 2p orbital and 3d orbital are same, and also 4f orbital. So which type of curve is obtained for 1s, 2p and 3d, 4f? So in 1s, 2p and 3d and 4f, only one peak is observed. So for example, number of peaks for 4f orbital, is equal to 4f orbital. So n minus l, 4 minus per l value per f orbital is equal to 3. 4 minus 3 is equal to 1. Only one peak is observed. But similarly 3d is also one peak, right? So similar diagram is observed for 2s and 3p and 4d and also 5f. 2p, 3p, 4d, 5f having same diagram. So in these orbitals 2 peaks are observed. So for 3s and 3s like 4p and 5d and 6f, all are having same diagram. So the number of nodes is number of peaks per radial distribution curve for an orbital is equal to n minus l. Number of radial nodes is equal to n minus l minus 1, n minus l minus 1. So for 2p orbital, here node is not present. For 2p orbital, what is the formula? Radial nodes is equal to n minus l minus 1. What is n value? 2. What is l value? The l value per p orbital is 1 minus 1. 2 minus 2 is equal to 0. For 2p orbital, number of radial nodes is equal to 0. So that means here this peak is not touching on the x-axis. Node is absent. For 3p orbital, this is one node. Okay, this peak is not touching on the x-axis. That means one node. According to formula, n minus L minus 1. This is the radial node. What is n value? 3 minus L 1 minus 1, n minus L minus 1. 3 minus 2, 1. So this is a one node, one radial node. Now for 3D orbital, here the curve is not touching on the axis, x-axis. That means its radial nodes are 0. So according to formula, n minus L minus 1. What is n value? 3. What is n value? 3. What is L value? L value per d orbital is, if L is equal to 0, that is s orbital. If L is equal to 1, that is the p orbital. If L is equal to 2, that is d orbital. 3 minus 2 minus 1. Right. So for 3D orbital, number of radial nodes is equal to 3 minus 2 minus 1 means 0. 3 minus 2 minus 1 means 0. So this is the radial node. Now we will discuss about angular nodes. Angular nodes is equal to radial nodes. Radial nodes is equal to n minus L minus 1. Angular nodes, n minus L minus 1. Angular nodes are nodal plane. Both are same. Angular node or nodal plane. Both are same. Angular node or nodal plane. Nodal plane is equal to azimuthal quantum number like L. So already says that s orbital does not having angular nodes due to s orbital is a non-directional. S orbital is a non-directional. That means the probability of finding electron around the nucleus is same in all directions. So that probability of finding electron is not dependent upon axis. That means its angular nodes are 0. Its angular nodes are 0 per s orbital. For any s, 1s, 2s, 3s, 4s, any s orbital having 0 angular nodes or 0 nodal plane. Why? What is L value? Per s orbital L value 0. So per s orbital angular nodes or nodal planes is equal to 0. Now for p orbital, right, for p orbital like 2p orbital. For 2p orbital, number of radial nodes already over. Angular nodes is equal to L value 1 is equal to 1. One angular node is present per 2p orbital. So right, for all p orbitals like 2p, 3p, 4p, any p, how many angular nodes are there? 1. So angular nodes are constant per one orbital or any p like 2p, 3p, 4p is 1. Why? Its L value is same. Now this is the p orbital. So this is the nucleus. So here the electron can revolve around the nucleus in two lobes around the nucleus. Right. These two lobes present on x-axis. This is the nucleus. These two lobes present on x-axis. So this is a z-axis and this is a y-axis. So here the probability of finding electron around the nucleus in two lobes on the x-axis. So this is appeared like a dumbbell. What is the shape of p orbital? Dumbbell. So here p orbital is present on x-axis, x direction. So this orbital we can say px. And in the yz plane, this is an imaginary plane. Here yz is an imaginary plane. In this plane, the probability of finding electron is 0. So the probability of finding electron is 0 in the plane that is said to be nodal plane. What is the nodal plane? Nodal plane is the imaginary plane. Nodal plane is the imaginary plane which is passing through the nucleus, where the probability of finding electron is 0, is known as nodal plane or angular node. So what is the angular node or nodal plane? The plane which is the angular node or nodal plane is a plane, imaginary plane which is passing through the nucleus, where the probability of finding electron is 0. So that is the nodal plane or angular node. Now here the px orbital having one nodal plane. What is that plane? YZ plane. Similarly, if we can take a py orbital, so this is, we can say, y axis or another diagram. So our y axis, this is, we can say, y axis, this is z axis, this is x axis. So here the probability of finding electron around the nucleus in two lobes on the y axis, that orbital is said to be py orbital, and here the probability of finding electron in yz plane, this is the yz plane, this is an imaginary plane, is 0. So sorry, not yz, xz, this is x axis. So xz, that is a nodal plane. One node py orbital, one nodal plane is there, that is xz plane. For pz orbital, we can say this is suppose pz, right, this is z axis. Here the probability of finding electron around the nucleus, this is the nucleus on z axis, so this is x, this is y axis. So here the probability of finding electron around the nucleus in two lobes on the z axis, but in yz plane, it is an imaginary plane, its probability of finding electron is taken as 0, So the pz orbital having one nodal plane, that is xy plane. So the nodal plane of px orbital is yz, the nodal plane of py orbital is xz, the nodal plane of pz orbital is xy. And here the one nodal plane, like xz nodal plane, is separated the two lobes on x axis. Here the yz plane is separated two lobes on x axis, that is px. So these are the angular nodes. If we can take a 3D orbital, so 3D orbital is the double dumbbell. What is the shape? Double dumbbell. So here dumbbells present on, suppose we can say this is x axis, this is y axis, like dx square minus y square. Here the two lobes present on x axis and y axis. So here the probability of finding electron around the nucleus is present in four lobes. This is one lobe, this is the nucleus, this is one lobe, second lobe, third lobe, four lobes. So this is, we can say, z axis. So here the probability of finding electron around the nucleus in four lobes. Here in p orbital 2 lobes, in d orbital 4 lobes. So but here in this plane the probability, what is that plane? YZ plane. This is the YZ plane. And this is the ZX. In this space the probability of finding electron is 0. Two planes, what are that? XZ and YZ. XZ and yz, xz and yz. So how many nodal planes are present in dx square minus y square? Two nodal planes. What are the dxz and yz? Dxz and yz. So in this plane, the probability of finding electron is 0. So all the d orbitals having 5 d orbital, d subcell having 5 d orbitals. What are the dxy, dyz, dzx, dx square minus y square, dz square. In 5 d orbitals, the 4 orbitals like dxy, dyz, dzx, dx square minus y square having 4 lobes. So here the probability of finding electron is present in 4 lobes. So all these 4 orbitals having 2 nodal planes. But if we can take a dx square minus y square, what is nodal planes? Xz and yz. Xz and yz. Okay, fifth d orbital, what is that? Dz square. In dz square, in dz square, like dz square, 2 lobes. This is the probability of finding electron. And another 2 lobes converts to ring. Another 2 lobes are converted to ring. So this is the ring. Another 2 lobes are converted to rings. So these are also present on x and y axis, these 2 lobes. So totally dz square orbitals in dz square orbitals, 2 lobes are present, another 2 lobes are converted to ring. So this is its nodal planes are 0. For dz square orbital, nodal planes are 0. So for dxy, dyz, dzx, ds square minus y square each having 2 nodal planes. For example, dx square minus y square having dxz and yz nodal plane. But dz square having 0 nodal plane, due to it is in 4 lobes, 2 lobes are present, another 2 lobes are converted to rings. So dz square orbital having 0 nodes. Now this is the radial probability distribution curves. Next goes to some problems are doing on this radial probability distribution curves.